Good morning, welcome to new lecture. Today I will look at more sample problem. We will see for different problem how we will approach to this problem and we will solve it. Assume we have one rod, composite rod, with different segments and different material. For example, we have rod between two supports, cross-sectional area is different and material properties even different. So for example, this is the first rod, second rod is here, and there is a small gap here, initial gap. I show with delta and this I, initial gap. So what we will do in this kind of problem and what we want to find in this kind of problem. For example, Young modulus, it is E1 for this part. Cross-sectional area, it is A1. A thermal coefficient of expansion, it is alpha 1. And the length, it is L1. For other part, other segment, I show with blue, it is E2. Young modulus, cross-sectional area, it is A2. Length it is L2. This system, this assembly, it is in room temperature. We will increase the room temperature or decrease or increase. Here we will increase it. So we have temperature variation delta T. Here in this example, we increase temperature from room temperature. How much we will increase? It is delta T. Delta T, it is certain value. It has magnitude and we know that. So we have composite rod, one part, it is from one material, another part from another material. As a result, Young modulus, it is not the same, it is different. Length, even in general case, it is different. And because material, it is different material. For example, one part it is steel, another part it is brass and or copper. So even thermal coefficient of expansion, it is different. If for this part it is alpha 1, for this part it is alpha 2. This assembly is in room temperature. We have to support here. This support keep this in equilibrium, but for another support there is initial gap. The magnitude of that initial gap, it is known. We increase temperature from room temperature. What will be the reaction in these supports? For example, the reaction, this is, I call it support number 1, here support number 2. What will be reaction in these supports? If I increase temperature, what will happen? We will have expansion. Total deformation, if I show with delta T will be equal to alpha 1 L1 delta T plus alpha 2 L2 delta T. If I factor out delta T, it will be delta T times alpha 1 L1 plus alpha 2 L2. So we have total deformation. We can calculate total deformation because coefficient of expansion for each part, it is known value, length is known value, thermal coefficient is known value. We can find total deformation if we know delta T, and we know delta T because we increase temperature from room temperature to certain value. We know delta T. So the first step we will find this total deformation. Then if total deformation is smaller than this gap, if total deformation is smaller than that gap, what will happen? We will have expansion, but this point, the end of this composite rod, will not touch the support. So if it is less than that gap or even it is equal to that gap, equal means barely it is touching. In that case, what will happen? We will have deformation, but we will not have any internal forces or internal stress. Internal force in each part, it is equal to 0. As a result, internal stress is equal to 0 and reaction, axial reaction will be 0 too. if it is smaller or equal to initial gap. But if it is bigger than that, if it is bigger than that means after expansion, this point, for example, point O, wants to move from right to left more, but this support will prevent, it will apply reactions. So that reaction will not allow to this point after reaching to this wall go further. So what will happen? We will have internal force and we will have reaction. So how we can calculate that internal force and internal, if we calculate internal force, we will able to find internal stress. Because if we able to find this reaction will transfer to this part 2 and part 1. So internal force in each part, they will be equal. But internal stress will not be equal because stress is force divided by cross-sectional area. Because cross-sectional area is different, stress will be different. So, in order to find that internal force, if total deformation is bigger than initial gap, in that case, delta T minus delta I. Up to cover this delta I, this gap, there is no force. After that, extra deformation, if I show that delta, this delta will cause reaction. So, assume this dashed line, this is expansion for part 1, we have expansion for part 2, and summation of expansion, it goes here. Up to here. Up to here it is delta I. Up to reach to this wall there is no stress or internal force. After that, total delta minus delta I means this delta will cause reaction. That reaction, how much is that? We don't know. I show with R1. I don't know the magnitude. I show with R1. But that reaction should return this deformation to initial position. So if we don't have this support, this will come here. After this wall line, it will go from right to left as much as delta. But because we have that wall will prevent, will not allow to, will not allow we have this delta deformation. So that reaction will return that delta deformation. If we have R1 reaction over at that point, that R1 will cause deformation in part 2. It will be R2 R1 times L2 over E2 A2 plus that R1, if we apply R1, internal force in this part it is R1. Internal force in this part it is R1 too, and reaction even here it is equal to R1. So internal force in each segment it is R1. So deformation of this part because of R1 it is this term. Deformation of part 1 it will be R1, L1, E1, A1. So I can write delta is equal to R1 times L2 E2 A2 plus L1 E1 A1. So from here I can find R1. R1 will be delta divided by this term, and because delta is equal to delta T minus delta initial gap value divided by L2 E2 A2 plus L1 E1 A1. So we can find reaction. If it is smaller, total deformation, it is smaller than initial gap, no reaction, no internal force, no stress. If it is bigger, we should calculate to see how much it is bigger, delta. That delta will cause reaction. That delta will create this R. That R should return this deformation to the initial point, should make this deformation equal to the zero. So if we don't have this R, it will move from right to left as much as delta. Now this R1 will cause equal deformation from left to right, and they will cancel that. So we should write this term, we should put equal, and I can find reaction. This is one sample problem. Another sample problem, let's look at this example. This example, again we have one rod with different part, and each part cross-sectional area is different. So something like this and like this. Again here L1, E1, A1. Here it is L2, E2, A2. And there is initial gap here. I can show with delta and with G. This system is subjected to external load. External load magnitude, it is P, and P it is known value, it is P. And the location of external load, it is point O. You see where is that? Okay, now we want to find reaction. How we will find reaction? Now, let's again, we should look at today two different scenarios. If we apply external load at point O, what will happen? Here this part, because this end is free before touching this support. Before touching this support, because this end is free, from here, for example, point A, B, C. From A to B, what is the internal force in that segment, in that part? Internal force in that segment, you see here is free, no force. If I move from A to B, in AB part, internal force is zero. So total deformation will be equal to deformation of part AB plus deformation of part BC. And because internal force in part AB is equal to zero, so deformation for AB part will be equal to zero, plus deformation for part BC will be equal to internal force in this part times length divided by EA. Internal force in BC part in this example, because I apply point P and point P is tension force, so I will have elongation at BC part, and internal force here, it is equal to the P, so it will be P times the length of that part, L1 over E1, A1. So total deformation will be P, L1, E1, A1. First step, we should calculate this total deformation. If the total deformation magnitude, it is less than or equal that gap value. This gap value, we know that gap. If it is smaller or even it is equal to that, what will happen? The reaction at this support, reaction A, will be equal to 0, because it will not touch this support. The reaction here will be 0. What is the reaction at point C? total external load will transfer to support C. And support C reaction should be equal in opposite direction because summation of forces in horizontal direction, it should be equal to 0. If it is not equal to 0, this assembly, this rod will not be in equilibrium. So RC in that case will be equal to the P. But if delta T total deformation is greater than that gap value, in that case it is different story. Why? Up to this support point, we apply this force, we have elongation at point BC. Up to here, to touch the support, up to touching the support, reaction RC is equal to the P, and here reaction is 0. But after touching that, this support will apply reaction and will have contribution against this external load. How much is that contribution? So, we can solve like this. We assume we don't have this support. If we don't have support, this is free to move. I apply load, so the total deformation will be deformation only for part BC. I can find total deformation. Total deformation minus that gap value, it covers this space. It will not create any reaction. But if this move more, that deformation will cause a reaction here. So that deformation, it is delta T minus delta gap. This deformation delta will cause reaction at point A. But because we have support here, this reaction will not allow to this rod move furthermore. So it will restrict here. So how much force should apply? We don't know. We assume it is unknown reaction A. That unknown reaction A, how we can calculate that? Unknown reaction A will cause deformation in inverse direction. In part 2 is equal to RA L2 over E2 A2 plus this RA will transfer to part BC2. It will be RA times L1 divided by E1 A1. So what I did, I divide this system to two different simple systems. Once the total deformation is bigger than delta gap in order to calculate reaction. I assumed first, in first step, I don't have support over there and I have this system and end is free, something like this. And we have external load here, P. I assume we have this. And I calculate that deformation for this system. Then, because in reality we have support here, I assume we have this system. And this system is subjected to only reaction. If we add these together, we will have initial example problem. You see, RA comes from here, it goes there. P from here, it will come there. So now we will look at this problem in two separate cases. One, we have external load. External load will cause deformation in BC part. That deformation is this much. From this deformation, delta G up to delta G, it will cover that gap, so will not create any reaction. Further deformation, more deformation, will cause reaction. That reaction will apply inverse deformation in opposite direction. That will be reaction times this length over EA of this part plus this reaction, because this reaction will transfer here, times the length of here divided by EA of that part. That deformation should be equal to delta 2. So from here we can find that RA. If we find RA, from here we have one equation, we have one unknown, so if I simplify here, even I can write delta is equal to RA L2 E2 A2 plus L1 E1 A1. So because we have all these, we can find RA. If we find RA, we can calculate RA. If we find RA, we know RA plus RC should be equal to the external load P. This comes from equilibrium equation. Summation of forces in horizontal direction should be equal to 0. If we find RA plus RC minus P should be equal to 0. If I take P to other side, RA will plus RC is equal to the P. So I can plug RA from here to here, and I can find RC is equal P minus RA. And here, because everything is known, so we can find RA as well. Let's look at another sample problem. We have one rigid beam. This rigid beam is pinned here at point A. At point B, we attach to one rod and that rod to the ceiling, and there is one small gap here again, delta G. The length from here to here, for example, L2, from here to here it is L1. The length for this rod, it is L3. Cross-sectional area, it is A. Young modulus, it is E. And this is rigid beam. Initially, this is horizontal. This is level beam and rigid beam. Then we apply one external load here. That external load magnitude is P. We know that. But we apply in somewhere, we don't know the location. We will apply in a location, in somewhere, so that after applying this load, what will happen? This load will create tension in this rod. Because of this tension, we will have elongation in this rod. So this point, for example, point O, will move down to point O prime. If this move down, this will rotate and close the gap. We want find X so that to close this gap, where we should apply this external load P in order to close this gap. This is problem statement. Assume we apply in one location, so the location X is unknown, where we should apply to close that gap. How we can find? Assume we will apply in one location like X. In order to close this gap, this beam should rotate respect to point O And after rotation, we will have this triangle. Here it is closing the gap, so we know how much this point, for example, if it is point B, will move down. BB prime will be equal to the delta gap because we want to cover that, we want to close that. How much this will move down? We don't know, but we can find from geometry. Assume it is unknown y. But in this triangle, look at to this triangle and this bigger triangle. Y divided by delta gap is equal to L1 divided by entire length L1 plus L2. From here, y will be equal to delta gap times L1 divided by L1 plus L2. Because we know L1, we know L2, we know the delta gap, initial gap, it is known value, magnitude, it is known, we can find y. If we find y, how much internal force in this rod? Internal force in this rod is equal to stiffness of that rod times deformation of that rod, which is y. The stiffness of that rod, it is EA over L3 times y. So we know Young modulus, we know cross-sectional area, we know the length, we can calculate the stiffness, times y, which we find here, f, now it is known value, we know f. I show with f star because it is known value. If f is known value, we can find the location of the external load P in order to close the gap. How we can find? If we know this f star, because we know the magnitude, and I take summation of moment respect to the A equal to the 0, what I will have? I will have this internal force, if I cut it in free body diagram like external load, and if I take moment respect to the A, F star times L1 will create moment counterclockwise minus P times the distance from here up to A. The distance from there up to A, if this distance it is unknown x, it will be L1 plus L2 minus x. So from here to here will be L1 plus L2 minus x, that distance. And because it is clockwise, I assume it is 0 is equal to 0. F is known, L1 is known, P is known, L2 is known, L1 is known again, L2 is known. So we have one equation, one unknown x. I can find the location of x, the location of external load in order to close that gap. One more problem, think about that up to next session. And it is very easy problem. My assumption you should be able to solve immediately, but think about that. I will solve next session. We have rigid beam. Rigid beam here, we attach to one support, hinge support. Here at this point we attach to two cable, one this point, another this point. This angle is 30 degrees. And this length from here to here, this length it is L. So this angle theta is 30 degrees. The length of this rod it is L. L it is known value. The length for this rigid beam again it is L. This is point O. At point O we apply external load. the magnitude of external load, it is known, is equal to P. So this is O, point B, point C. We want to find the ratio of force in OB divided by force in OC. So if I apply external load at point O, if I pull down point O, what will happen? This rigid beam will rotate respect to point A, for example, and we will have deformation here. We will have vertical deformation as much as delta. Because of this deformation, definitely we will have tension in OB and OC. So what is the ratio of internal force in member OB divided by internal force in member OC? Think about that. I will solve next session. Thank you so much for watching this lecture. See you next session. Bye bye.